Hey guys, now I'm just going to continue the stuff I did earlier on today, and we're going to work out a solution for the Verhulst equation. Okay, so what we did in the last video is we kind of came up with a nice expression here, which you can, as you can probably imagine, sort out even more in order to find the solution to the Verhulst equation. So what I'm going to do now is I'm just going to kind of place this paper on top so we can copy it easier, like more easily. So we have here ln of n minus ln of 1 minus n over k equals rt plus c. Now we can apply very basic logarithm rules in order to simplify this, and so we can say now that ln of n minus ln of 1 minus n over k is the same thing as, well, first of all we're gonna establish that n and k are always greater than 0, because or greater than equal to, they can't be negative. Like, you can't have a negative population, and so you can't have a negative capacity, because capacity is just the terminal stage of the population. So we established that, so we don't need the moduluses anymore, so we can just say that this is the form we can rewrite it as. Okay, that's sorted. But now we have to kind of press on with that now. So using logarithm rules, we can say that actually this expression over here is the same thing as saying ln of n divided by 1 minus nk, because you see we have a first logarithm, a second logarithm. If it is a minus sign between them, we can just do division of the argument of the first one by the second one within that ln. So here we have that, and that's equal to rt plus c. And remember, c doesn't really matter at this point, we just know it's a constant of integration, which is integration for both sides. So we can go on and actually do e to the power of that times e to the power of that. And in that we'll get n over 1 minus n over k equals e rt times e to the c. Now, again, e to the c doesn't really matter. You can just write c. Okay, because e to the power of c is going to be a constant. A constant to the power of a constant is another constant. So, so then n over 1 minus n over k equals, let's just say c times e to rt, cert. Okay, now we can actually go on and reciprocate everything, and we get 1 over n divided by k over n equals c, reciprocal of c, it's another c, it doesn't really matter, times e to the minus rt, remember. And now we can kind of manipulate this fraction in a funny way. Cross out n here, cross out the n here, then it's 1 over n minus 1 over k equals this, okay? Now what we can do is, we can write 1 over n equals ce to the power of minus rt plus reciprocal of k. Why is that important? That's important because we can inverse everything here, and we will get n, or let's say it's a function of time, right? Because that's what it is. We're measuring the growth population over time. It's equal to 1 over this thing over here plus reciprocal of k. Okay, that's good. Now, how do you find an expression for the initial population? Remember, according to this model, initial population is just going to be the population at time equals 0. So at t equals 0, we say, we call it n0 by the way. It just sounds better, facilitates everything. It's equal to 1 over c to the e0 plus 1 over k, which equals, remember this is 1, anything to the power of 0 is 1, so just 1 times c plus 1 over k. That implies that inverse of initial population equals c plus inverse of k, which implies that c equals to 1 over n0 minus 1 over k. Now this is important because they're going to substitute in to the other equation we derived. And so I'm going to grab another piece of paper. Just flip it. I hate it when in maths you've got so many sheets and you have to transfer notes from one sheet to another. I just hate it. Anyway, let's just establish with c equals. Let's just establish with c equals 1 over n 0 minus 1 over k, because that's basically the takeaway from here. Yeah, I think, yeah. Okay, and then obviously we have the equation itself, which is n of t equals 1 over ce minus rt plus inverse of k. Yeah, we established that. Okay, so then what we do is we go on and just manipulate this algebraically to make it look better. So n of t equals 1 over, substituting it in, just writing 0 minus 1 over k times e to the minus rt plus 1 over k. Okay, fair enough. And then from here we can actually go on and multiply by 1, do it very cunningly in order to make it look better, in which case we would end up with n0k and here k gets cancelled out because there's a k here, n0 becomes, and from here we multiply the n k plus times here, and then we end up with this being cancelled out, this being cancelled out, which is very nice, very convenient. So what we do now is, and we just rewrite it as a simplified version of this malarkey here. So that's k minus no times e to the minus rt plus, this is a plus, not a t. Yep. And this is very useful because we can cancel the n out. And by the way, this form is really good, but I'm just trying to make it look even better. We can say that, like, this is a really kind of prevalent form of this equation solution. We can use it and it's fine. But I personally like simplifying it a bit more. So I like crossing the n out. Or maybe it's not simplifying necessarily, but I don't know. I find it's better that way. So you can actually go on and write this as dividing this, removing this no, and then actually going on and writing k over n0. Then you can say n of t equals k, so some constant times, divided by the initial population minus, over, so k over the initial population minus 1 times e to the minus rt, and then that's it, because, well, plus 1. And then from here we can actually, I'm not sure if it's necessarily a better thing to do, but I personally find that if you kind of minus it, it looks better. But I don't know, I think this is good enough. Yeah, I mean, you will see this equation in so many forms. It's the same sigmoid kind of shape, but so you could see it as this. Which is kind of reminiscent of another form which you might see, those of you who do high-level maths and neural networks, you might see you might see it as, sorry, it's not an equality sign, but it's equivalent to another form known as the sigmoid function. Let me just check, I'm not entirely sure. I think it's e to the power of minus x plus 1. I'm not sure, but you see that's one form. Or alternatively, you might see it as the logistic map. Now, the logistic map is very important in chaos theory. I want to make a video about it one day, but yeah, anyway, the logistic map is a very interesting recurrence relation, which is used a lot in chaos theory. It's essentially this, right? It's like a logistic equation, but instead of having a derivative and like all the differential equation features, so it's a series, a sequence. And what's interesting about that is at some point it begins not having a kind of set regulated value, but jumping back and forth between values and ending up creating really weird patterns, which we would later know as pseudo-random number generation. And that's kind of when we have a certain pattern which is not necessarily random, but in fact is deterministic, but really hard to foresee unless you know the initial values. And that's how calculators come up with random numbers. But yeah, so this equation is really, really useful. As you can see, it's kind of what we can see happening in terms of the reported amount of cases of coronavirus in the world. That's what happened with the Spanish flu, that's what happens with most viruses. And it's quite important to understand that those viruses don't just rise exponentially, right? They can't keep spreading forever. So yeah, hopefully that gave you some hope. It's an interesting bit of maths, and yeah, I think it's worth making a video about it. So I'll see you in the next video, and keep safe, stay at home, and do some more maths.